Hello students, in today's video we will discuss the method to find particular integral of given homogeneous linear partial differential equation with constant coefficient. First we discuss a particular method to find particular integral, that is a short method. We have already studied, which is in which right hand part, which is function of xy, is a particular type, that is it was of function of ax plus by. Now we will discuss another particular method when right hand part, which a function of xy, is in the form of x raised to power m, y raised to power n. If given function is of such type, then we can apply some particular method to find particular integral. In this case, to evaluate pi, we evaluate pi by expanding function 1 upon f d dash is in an infinite series of ascending powers of d or d dash. Means we are given with the equation f, capital F, d of d dash is equals to function of xy, where function of xy is in the form of x raised to power m, y raised to power n type. M may be 0 or greater than 0 positive integral power, and similarly n might be 0 or positive integral power of y. Now here what we do, we just take either d or d prime, taking outside highest power of d. When we take highest power of d outside, the remaining function convert into the terms of d prime upon d types. But if we take d prime outside, highest power of d prime outside, the remaining function convert into d upon d prime, and we shift this function into numerator part, whose power is -1, and using binomial expansion we expand it into an infinite series, and then we can find particular integral of right hand part. For better explanation, just try for some example. Suppose we have a problem d square minus a square d prime square z is equals to x. Here capital D is del by del x and d prime is del by del y. First we write its auxiliary equation to find complementary function. Its auxiliary equation is m square minus a square equals to 0. It gives us m is equals to plus minus a, and about m is equals to plus minus a, the complementary function will be phi 1 y plus ax plus phi 2 y minus ax. And now we find particular integral. Particular integral will be 1 upon d square minus a square d prime square of x. Now here we will take d square outside. When we take d square outside, here remaining term is 1, and second term becomes minus a square d prime square upon d square. Now we shift this term into numerator. By shifting it into numerator, it becomes 1 upon d square outside into 1 minus a square d prime square upon d square whole power minus 1 over x. Now using binomial expansion, we expand this term into infinite series. So it becomes 1 upon d square into 1 plus a square d prime square upon d square, plus next term would be a for d prime raised to power 4 upon d raised to power 4. Here in numerator we have, if d, it means differentiate this function with respect to y, or if we have d in numerator, it means differentiate the function with respect to x. Now similarly, if we have d in denominator, it means integrate given function with respect to x, or if we have y in d prime in denominator, it means integrate this function with respect to y. So first we open it and we get here x plus a square d prime square upon d square over x plus so on. Now first we apply d prime over x. It means differentiate x with respect to y. It gives us 0. Or if we apply first integrate, it gives us x into some function of y, and after that if we differentiate with respect to d prime, ultimately it gives us 0. So we get 1 upon d square x plus a square 0. Now we integrate this x with respect to x. We get x integration of x twice, we get x cube by 6. So its pi is x cube by 6. And general solution will be z is equals to cf plus pi, that is z is equals to phi 1 y plus ax plus phi 2 y minus ax plus x cube by 6. Here phi 1 and phi 2 are arbitrary function. Let's take another problem. D square plus 3d d prime plus 2d prime square z over equals to x plus y. Here auxiliary equation is m square plus 3m plus 2, and its roots are m is equals to minus 1 and minus 2, and about these roots complementary function can be written as phi 1 y minus x plus phi 2 y minus 2x. Now we discuss particular integral. It's given by 1 upon d square plus 3d d prime plus 2d prime square x plus y. Here we can take d square or d prime square. Any one of d square or d prime square we can take outside. Here we take 2d prime square outside. So we get 2d prime square outside into 1 plus 3 by 2 d upon d prime plus d square upon d prime square. Here it becomes 1, as we take 2d prime square outside, it becomes 1. It becomes 3 by 2 d upon d prime, as 1 d prime cancel out, and here it becomes d square upon 2d prime square over x plus y. Now shifting this part into numerator, it becomes 1 upon 2 d prime square into 1 plus 3 by 2 d upon d prime plus d square upon 2 d prime square, its power minus 1 x plus y. Now open this using binomial expansion. 1 minus this term, then plus its square over x plus y. Now we multiply this function, so it gives us x plus y, and now we operate this term over x plus y, we get minus 3 by 2 d over d prime over x plus y plus 0, as this term is of first order, and when we differentiate it twice, it gives us 0. Here d means differentiate with respect to x. We are to differentiate x twice with respect to x, it gives 0. We are to differentiate y twice with respect to x, it also gives 0. So now we differentiate this term with respect to x, it gives us 1 and it gives us 0. Now we integrate this 1 with respect to y, it gives us y. So it becomes 1 upon d prime square over x plus y minus 3 by 2 y. Now we integrate this whole term with respect to y twice. So 1 by 2 x y square by 2 plus y cube by 6 minus 3 by 2 y cube by 6. Here 1 by 2 is already here. It's 2. So it becomes 1 by 2 x y square by 2 minus y cube by 12, or general solution will be cf plus pi, which is z is equals to phi 1 y minus x plus phi 2 y minus 2x plus 1 by 4x y square minus 1 by 24 y cube. Let's take one more problem. D square minus 2d d prime plus d prime square z is equals to exponential x plus 2y plus x cube. First is auxiliary equation is m square minus 2m plus 1. It gives us 2 root m minus 1 whole square equals to 0. M is equals to plus 1 and plus 1. So CF is equals to phi 1 y plus x phi 2 y plus x. And particular integral is 1 upon d minus d prime square of exponential x plus 2y plus x cube. Now we will find particular integral in two parts. First we will find particular integral for exponential x plus 2y, and then we find pi for x cube. So separately, one by one, we solve both. So first, 1 upon d minus d prime square exponential x plus 2y. This is a case of particular case of finding pi when given function is of the form ax plus by type. Here a is 1, coefficient of x, b is coefficient of y, that is 2, and taking ax plus by as v. So it becomes 1 upon f of ab. Replace d with a and d prime with b. It is 1 minus 2 whole square. It gives us 1. And integrate exponential v twice. Twice means which is the order of given homogeneous equation. It's order of 2, so we will integrate it 2 times. So it becomes double integration exponential v with respect to v and b. It gives us exponential v, which is equals to exponential x plus 2y. So particular integral of exponential x plus 2y is exponential x plus 2y. Now we will find particular integral of x cube. This is a particular case of second time. Here we will take d square outside. So it becomes 1 upon d square, 1 minus d prime upon d whole square. Now shifting this part into numerator, it becomes 1 upon d square, 1 minus d prime upon d whole power minus 2x cube. Now using binomial expansion, we will expand it into infinite series. So its first term is 1 plus 2 d prime upon d, second term is 3 d prime square upon d square, next term is 4 d prime cube upon d cube, plus next term is a term containing a derivative of fourth order. When we differentiate x 4 times x cube, it gives us 0. Now we will first differentiate x cube with respect to y. It already gives us 0. So all these terms gives us 0, as there is no term of y appearing here. So it gives us 1 upon d square x cube only, which is equals to x raised to power 5 upon 20, as we are to integrate x cube twice with respect to x. When we integrate it, it gives us x 4 upon 4, and further when we integrate it, it gives us x raised to power 5 upon 20. So particular integral will be exponential x plus 2y plus x raised to power 5 upon 20. So z is equals to 5(1) y plus x 5(2) y plus x plus exponential x plus 2y plus x raised to power 5 upon 20. This is general solution for given equation. And here phi1 and phi2 are arbitrary constant.